Welcome, fellow chemists, to the 6th video on the reactions of the alkenes, where we take a look at oxymercuration and alkoxymercuration-reduction. Where previously acid was used to catalyze the addition of water in the formation of an alcohol, a mercury-based compound will be used this time. You can see that the result is the same, but this method does have the advantage of not exposing the original molecule to acidic conditions. The acid-catalyzed addition of alcohol to form an ether was similar to that of water, and the same is true for the mercury-based route. The final product distribution still favors tertiary over secondary over primary, but we will encounter one big difference later. The first step in oxymercuration is the mercury acetate reacting with the alkene. While it is a different process, it should look vaguely familiar to you. Very quickly, the mercury has accepted a pair of electrons, donated one of its pairs, and lost a pair of electrons to one of its acetate groups. Where before we had a chlorine in this position, now it is a mercury atom that has acquired a positive charge, so it acted as an electrophile. In order to balance this positive charge, we have the negative ion, which is one of those acetate groups. This ion will play an important role later. So once again, we have a positive ion that is not a carbocation. It is a mercurinium ion. This ion will be attacked by the water molecule, which adds to the original sp2 carbon with fewer hydrogens. The positive charge ends up on the oxygen of the water. The acetate ion lost by mercury earlier comes back and removes the proton from the ion, leaving the alcohol group on the molecule. We are used to intermediates, but most of them have had some sort of charge. But we now have an organomercury intermediate with no charge, so how to get rid of it? The addition of the alcohol group and mercury portions means oxymercuration is complete, so we move on to reduction. In organic chemistry, this often involves increasing the number of carbon to hydrogen bonds at the expense of another atom. This can be accomplished using sodium borohydride. Do not concern yourself with how this occurs, it is a bit of hocus pocus, or a story for another day. When the magic of the reduction process is complete, we have our expected alcohol product. The acid-catalyzed additions of water and alcohol were virtually identical, and the same is true now. The mercury acetate is replaced with mercuric trifluoroacetate to increase efficiency, but the mechanism is otherwise the same. I will show the detailed animation, but keep in mind you can apply the ideas to adding water too. Mercuration starts with the mercury interacting with the alkene itself. This forms the positive mercurinium ion, as well as a negative trifluoroacetate ion. Alkoxy begins when the alcohol adds to the carbon with fewer hydrogens. It concludes when the trifluoroacetate lost earlier removes the proton, leaving an ether group on the organomercury intermediate. Once again, sodium borohydride is used for reduction, transforming the carbon-mercury bond into a carbon-hydrogen bond. The final product, as expected with the addition of an alcohol on an alkene, is an ether. Once again, we must consider the regioselectivity of this reaction. Switching back to oxymercuration, what would you predict the product of this reaction is? Without describing the entire mechanism, the water, or more specifically an OH group, ends up on the secondary carbon, while the hydrogen from the sodium borohydride ends up on a primary carbon, and the product is an alcohol. But why was there no rearrangement with this process? We form a secondary alcohol, but if a hydride shift occurs, we get a tertiary alcohol. The reason no rearrangement occurs is because we form a mercurinium ion, not a carbocation, and we cannot rearrange mercurinium ions. The reason behind the regioselectivity, though, has to do with the transition state. When the water attacks the mercurinium, it can do so in one of two places, meaning there are two possible transition states. If it approaches the less substituted primary carbon, a bond begins to form with the water and one is breaking with the mercury. However, if it attacked the more substituted secondary carbon, the transition state is more stable. As we have seen before, the more stable something is, the greater influence it will have on product formation. Therefore, in this case, the water attacking the secondary carbon results in a more stable transition state, and thus the alcohol group lands in that position. In summary, the oxymercuration process begins when the mercury acetate reacts with the alkene, forming a mercurinium ion. Water then attacks the ion and bonds to the original sp2 carbon with fewer hydrogens. Another water removes the additional proton, leaving us with an organomercury intermediate. Finally, reduction occurs through a reaction with sodium borohydride. The mercury is removed and replaced with a hydrogen. The product, as expected, is an alcohol. In alkoxymercuration, the mechanism is essentially the same. The differences include: first, mercury acetate is replaced by mercuric trifluoroacetate. Next, an alcohol attacks the mercurinium ion, and then another alcohol removes the additional proton. And finally, after reduction, the final product is an ether. The regioselectivity of both processes favors tertiary over secondary over primary for the locations of alcohol or ether groups. Coming up, we will investigate hydroboration oxidation, in which, once again, we do not concern ourselves with carbocation intermediates. However, we do get to flip the script on typical product distribution. Thank you very much for watching. If you enjoyed this video, please like and subscribe as I have more in development. If you want to refresh your memory on the acid-catalyzed mechanism of adding water or alcohol, check out these previous videos. As usual, feel free to get in touch with me via email, social media, or if you would like, make a request in the comments.